In Cycle 2, Lesson 18, we're going to put angles on the Cartesian plane so that we can then deal with angles that are greater than 90 degrees. Everything we've done up to now, we just had standalone triangles where we had a right angle within it, which meant that all our angles that we were dealing with had to be between 0 and 90 degrees. But we can, with a little bit of an extension, we can make this, we can extend it to the Cartesian plane and actually go up to 360 or more as far as angles go. So if we want to put angles on the Cartesian plane, here's what we do as a standard sort of procedure. We start at the origin. So our angle is always measured from the origin. And so we have what's called an initial arm. That's the one that's always on the x-axis, the initial arm. And then we rotate from there a certain angle, a certain number of degrees. And so here's an illustration of a particular angle, which we often call theta. We use the symbol theta to represent that, until we get to what's called the terminal arm. Just terminal as in that's where the angle stops. So the angle's between those two arms, and it's centered at the origin. That's called standard position. We can also rotate in two different directions. By convention, if we rotate in a counterclockwise direction, that's called a positive angle. If we rotate the opposite way, so if I was to start here, always starting the initial arm, but to go around this way, then that would be a negative angle. We'd measure that, we'd put a negative sign in front of that angle. Now remember, the full rotation around in a circle is 360 degrees. Therefore, half a circle is 180 degrees. So if I was to do an angle from, say, here to here, that'd be a 180. Or a quarter of a circle is 90 degrees. So if I started at my initial arm and went to the y-axis, that would be 90 degrees. And then an eighth of a circle is 45 degrees. So we can break it down. Here's some different terms that we should know. Just a reminder that we can break the Cartesian plane down in different quadrants. Top right is quadrant 1. That's where both x and y values are positive. Then we go counterclockwise. Quadrant 2 is top left. Quadrant 3 is bottom left, where both the x and y values are negative. And quadrant 4 is bottom right. The principal angle is always the angle that is between the terminal arm, between the initial arm and the terminal arm. But there's another important angle. Once we get beyond 90 degrees, as you can see in this sketch we are, if we were to measure between the x-axis and the terminal arm, that's called the related acute angle. We're going to use that in some of our calculations. So pay close attention to what I'm saying at this point. The related acute angle is always between the terminal arm and the x-axis. The x-axis, never the y-axis. The related acute angle is never between the y-axis and the terminal arm. It's always between the x-axis and the terminal arm. So if it's in quadrant 2, it'd be something like that. If it was in quadrant 3, then the related acute angle would be in there from the x-axis. If it was in quadrant 4, then the related acute angle would be in there. Related acute angles, by the way, are never negative. You can see that I've drawn some arrows going in the negative direction for the related acute angles, but they never are negative. When we're talking about related acute angles, all we're ever talking about is just the magnitude of them, but not the direction they're going in. So, sketch each angle in standard position. All right, so if we know that something is 120 degrees, again, we're starting from the initial arm on the positive x-axis. We know from here to here is 90 degrees. 120 would be another 30 degrees beyond that. So that's one way I could think, okay, it's about here. Another way I could think about it is from here to here is 180. So if I want to draw an angle of 120, I should put an angle of about 60, my related acute angle, in here. And so I know that an angle that looks like that is about 60, so I can draw it like that. 225, again, starting from the initial arm, from here to here is 180, but I have to keep going. 225 is the same as 180 plus 45 degrees, right? So again, if I keep going past 180, then it's going to end up in the third quadrant. And my related acute angle, I didn't give myself a lot of space here. Let me go do it over here. The related acute angle in this case would be 45 degrees, the angle between the x-axis and the terminal arm. Negative 135 degrees means I still start at my initial arm, but negative tells me to go backwards until I've done 135 degrees. So from here to here is 90 degrees. If I keep going, though, until I've covered 135 degrees, I get here. And I've got the same related acute angle, because if I kept going all the way to the x-axis, that would be negative 180. So 45 plus 135, ignoring the negative sign, gives me 180 degrees for a half circle. Notice how these two are exactly the same terminal arm. They're really the same angle. They're just being measured in a different direction. But they get to the same terminal arm. Principal angles are angles between 0 and 360. So if we're talking about principal angles, we're not talking about negative angles. And the reason it's between 0 and 360 is because 360 is one full rotation around the Cartesian plane, right? If I were to keep going, I could keep going. I could go around as many times as I want, but we're repeating ourselves. Remember this idea of periodic functions? Once I've gone past 360, I start over and I'm just repeating myself, so I don't need to do that. So which of the two angles in example 1 are principal angles? Well, A and B are. C isn't, because it's negative. It's going the wrong direction to be a principal angle. Co-terminal angles are angles with the same terminal arm, but different direction of rotation. So B and C here are co-terminal angles. They both have the same terminal arm there in quadrant 3, but they're different angles, but they really represent the same terminal arm on the Cartesian plane. So another example of co-terminal angles would be, say, 210 degrees. So where would 210 be? Start on the initial arm, go around, there's 90, 180. Well, 210 would be 30 degrees past 180. It would be around here somewhere, wouldn't it? My related acute angle would be 30 degrees, but 210 would be going this way. But if I were to go this way, that would be negative 150, but it takes me to the same terminal arm. Or 570, well, if I were to start here and go all the way around, there's 360, 450, 540, 570 takes me to there. So those three angles really all end in the same terminal arm. So determine the principal angle. Remember, that's going to be an angle between 0 and 360 degrees, but it's going to have the same terminal arm as this one. So if it's a positive angle, like A part is, I can just subtract multiples of 360 from it. So the principal angle would be this angle minus 360, which is 39 degrees. That'd be if I went all the way around once and then stopped about here. Negative 100, if I'm going backwards, it's what's going to add up to 360. So if I had 360 minus 100, I got 260 degrees. That's going to be, I want to subtract them in this case. Try and find a place to draw a picture. I'll draw it up here. Negative 100 degrees would be here, but positive 260 would just be coming at it from the opposite direction. And negative 720, let's picture this one first. So I'm going all the way around negative 360, go all the way around again. I'm at negative 720 once I get back to my initial arm. That's going to be the same as 0. Or I could say 360, because 360 is also considered a principal angle. But 0 and 360 are really the exact same angle. They both land you back on the initial arm. So I've already talked a little bit about related acute angles. those are angles that are always in relation to the x-axis, never the y-axis, as I tried to point out before. And it's the angle formed between the terminal arm and the x-axis. And it's always a positive angle. So whichever direction we measure it, we still call it a positive angle. It's always going to be between 0 and 90. That gets us the acute part. Sometimes it's useful to know what the related acute angle is, the angle between 0 and 90, because then we can do our trig ratios on it. So to determine the related acute angle in each case, well, if my initial principal angle is 150, that's going to take me up to, it's going to be about here. Again, I know it's all the way to the x-axis again would be 180 degrees. So the difference between the 180 and the 150 is 30. My related acute angle in this case is 30 degrees. In this case, 315 degrees, so I start, go all the way around, there's 270, 315. It's going to take me to about here. There's 315 degrees. So to go to the rest of the way to the x-axis, beta would be 45 degrees. 45 plus 315 would get me 360, which would be a full rotation. And again, doesn't matter which direction I'm measuring it, related acute angles are always positive. Negative 135 means I start on the initial arm, I go this way, down to here is negative 90. I go another 45 degrees to negative 135. My related acute angle is from the x-axis, of course, and it's always positive. So 45 degrees plus 135 would be 180. And again, I'm ignoring the negative sign on the 135. It's just the magnitude of 45 degrees for my related acute angle. State the principal angle for a given related acute angle and give the quadrant. And given quadrant, sorry. So if I've got a 71 degree related acute angle in quadrant 3, that means 71 degrees is here, but I'm measuring all the way from here, so it's 180 plus 71 gives me 251 degrees. 45 degrees in quadrant 6? No, I think that was supposed to say quadrant 4. There's no quadrant 6. So in quadrant 4, a 45 degree related acute angle would be down here. And the principal angle would be coming all the way around here, so it would be 360 minus 45 degrees, which would be 315 degrees. 89 degrees in quadrant 1. If things are in quadrant 1, they are what they are. The related acute angle is going to equal the principal angle, because in quadrant 1 we're only going between 0 and 90 anyway, aren't we? So the principal angle in this case would be 89 degrees, same as the related acute angle. So that's always going to be the case in quadrant 1. The following relationships also occur between trig ratios depending on which quadrant the angle is in. So the terminal arm of the principal angle, if it lies in quadrant 2, is 180 minus theta is going to be sine 180 minus theta equals sine theta. So what are we trying to say here? They're trying to point out that there's certain connections. Sine, because it's measured on the y-axis, is always opposite over hypotenuse. So let's make this into a triangle. Just pretend that it stops here. So sine is opposite over hypotenuse, and cos is adjacent over hypotenuse. And so if I make these angles over here, let's think about what's the same between these two angles and what's different. The opposite is the same for either one of those angles. They're both measured above the x-axis, they're positive y values. Hypotenuse is always positive, We never measure that as a negative angle, so that's the same no matter what. However, the adjacent side, this one's measured on negative x-axis, whereas on this quadrant over here, it's the positive x-axis. So what this is trying to say is that sine theta, which would be measured over in this quadrant here, is going to be the same as sine 180 minus theta, which is this triangle over here, because of what I was just saying, how the opposite and the hypotenuse are the same in those two triangles I just finished circling. Whereas cosine is going to be opposite. The cosine of this triangle here is going to be the opposite sign for the cosine of this triangle here, because the x's are opposite signs. So cosine is x, or adjacent over hypotenuse in quadrant 1, and it's a positive value. And in quadrant 2, the x value, the adjacent, is going to be a negative value. So they're opposite signs compared to each other. Likewise for tan, because again, the x values are negative in quadrant 2, and tangent comes from doing opposite over adjacent. So we'd have two positive values here in quadrant 1, opposite over adjacent, whereas I'd have positive opposite over negative adjacent in quadrant 2. So again, they're opposite signs, and that's what this is getting at. So this is trying to show you that they're actually the same, but they're opposite signs. And the same thing's going on in quadrant 3, except that now in quadrant 3, both the y and the x are negative. We're measuring it on the negative x-axis and the negative y-axis compared to positive y and positive x here. So opposite over hypotenuse is going to become negative in quadrant 3. Opposite, adjacent over hypotenuse is also going to be negative over in quadrant 3. But in quadrant 3, we're going to have opposite and adjacent be negative. So negative over negative is going to make a positive tangent. So we'll end up with the exact same tan when those two negatives cancel out in quadrant 3, because of that fact that they're both negative. And in quadrant 4, once again, if we compare these two triangles, now we've got a positive y in quadrant 1, but their same triangle in quadrant 4 would have a negative y. They both have the same x, but that positive x, and of course the radius is the same. So hypotenuse, when I have a negative y, is going to give me a negative sign in quadrant 4. Because the x is still positive in quadrant 4, it's going to stay as a positive cosine. And tangent, because only the y is negative in quadrant 4, but the x stays positive, is going to give me a negative tan. So the upshot of all this is that when we do trig ratios using the related acute angles in different quadrants, what happens is that in quadrant 1, sine, cos, and tan are all positive. All trig ratios are positive. In quadrant 2, the sine is positive, as you can see here, but cos and tan are negative, okay? So only sine is positive. I'm going to say sine plus for positive. Now I'll write it out, what the heck. Sine positive. In quadrant 3, you can see that only tan, where's quadrant 3? Quadrant 3, only the tan is positive. Sine and cos were both negative. So tan is positive. And in quadrant 4, only the cosine is positive. Sine and tan were both negative in quadrant 4. So cosine is positive. That's going to come in handy. It may seem a bit bewildering why I'm pointing this out at this point. I'm looking ahead to some work we're going to do in the future. So for now, try to wrap your head around that, and it's going to come in handy for stuff we do later. There's a way to remember what's positive where. If we take the first letter of each one of these things, and then we start down here in quadrant 4 and go this way, it spells the word cast. And so you're going to hear people, me, and in other math courses, people talk about the cast rule. That's just telling you, it's an acronym to remind you that if you start in the bottom right quadrant, quadrant 4, and spell out the word cast, that the letters tell you what's positive, which trig ratios are positive in different quadrants. So in bottom right quadrant, only cosine's positive. In quadrant 1, the top right, all trig ratios are positive. Quadrant 2, only sine is positive. Quadrant 3, only tan is positive. And we're going to work with that more in the future. So keep that in mind.